Many ancient marvels are more than just beautiful, they provide great examples of geometry. We can use pyramids to explore the Pythagorean Theorem. We can see properties of this theorem in ancient architecture from the Egyptians to the Maya. In pyramids, adjacent sides of the three-dimensional figure match where they come together. To determine the lengths of these matching edges, the Pythagorean theorem comes in handy. If you know the length of the base and the height, meaning two sides of one right triangle, then you can calculate the length of the third side with this theorem. In a right triangle, two legs form a right angle, and the hypotenuse is the side opposite the right angle. If A and B are the lengths of the triangle's legs, and C is the length of the hypotenuse, the Pythagorean theorem's equation is a squared plus b squared equals c squared. Let's look at the world-renowned Great Pyramid of Egypt and figure out the edge's length. If we have some of the measurements, the Pythagorean theorem can provide us with a way to get the answer. So let's focus on one of the pyramid's faces. See how it can be divided into two right triangles? We can use the Pythagorean theorem to calculate the length of the edge if we know the triangle's base and its height along the face. Each triangle's base length is 378 feet, and the height is 612 feet along the face. Then what's the length of the right triangle's hypotenuse, the edge of the pyramid? Plug our numbers into the equation a squared plus b squared equals c squared. Here, a is 378, b is 612, so 378 squared plus 612 squared equals c squared. Then we calculate c squared, and then take the square root to get c. We get 719 feet for the length of the edge. All the sloping edges of the pyramid will have the same measurement because the faces of the pyramid are congruent isosceles triangles. The Pythagorean theorem can allow us to calculate one side of a right triangle if we know the lengths of the other sides. So how do we know this theorem works? Here's an informal proof. Look at this right triangle with sides of lengths A, B, and C. Now, see these two squares? They have sides of lengths A and B. Together, the two squares' area equals a squared plus b squared. Divide the double square figure to make two triangles like the original one. Now we'll swing these inside triangles up, pivoting them about their highest points. See how they all fit into a square with sides C? This square's area is c squared. We can now understand that the area of the first two squares, meaning a squared plus b squared, really does equal c squared. Voila! An informal way to prove the Pythagorean theorem. There are gadgets for everything these days. And with the push of a button, it's possible to go from being completely lost to pinpointing exactly where you're standing in the world. This can be done with the Global Positioning System, known as GPS. It uses triangulation, calculations using geometric principles of triangles to find you. The beam goes between a satellite in space, the ground station, and the receiver. Triangles can help us figure out a distance using the Pythagorean theorem. It describes the relationship between the leg lengths A and B of any right triangle and the length of its hypotenuse, C. The theorem is a squared plus b squared equals c squared. In Washington, D.C., streets run north-south, east-west, and some diagonally. This can form triangles with the other streets, which are at right angles to one another. Let's figure out how to make the most of your time. Like in many cities, seeing Washington, D.C.'s most popular sites is a challenge. They're spread out across town. Luckily, the diagonal streets are helpful. Cities like Washington and Paris are unique. There's the option of taking a diagonal route between the sites, for example, the White House and Georgetown. Suppose you want to find the difference in distance between the diagonal Pennsylvania Avenue route compared to strolling along the north-south, east-west streets. Let's say you're told that the distance to M Street on 16th is about half a mile. And from there, it's about 1¼ miles to Georgetown at 29th and M Streets. To find the length of the diagonal to 29th and M, plug the numbers into the equation a squared plus b squared equals c squared. Here, a is 0.5 miles, b is 1.25 miles, so 0.5 squared plus 1.25 squared equals c squared. So we calculate c squared, and then take the square root to get c. That's about 1.35 miles for the length of c. Taking the perpendicular roots, about 0.5 miles plus 1.25 miles, totaling about 1.75 miles. The difference is about 1.75 minus 1.35 miles, or around 4/10 of a mile. To save time, it makes sense to take the diagonal root. Math can help at unexpected moments. If you're about to set sail and plan on a safe journey, one of the many details to take into account is the sail. Before shipping out, let's take a closer look at the sail's shape. The wind pushing on the sail's surface transfers a force to the sail, and then to the boat it's attached to. This force propels the boat. Often, a sail has the shape of a right triangle. So, if a friend asked you to install a new sail, you need to know its measurements. In sailing terms, the two legs of the triangle are called the luff and the foot, and the hypotenuse is called the leech. But let's say your friend only gave you the luff and leech measurements, and you need to figure out the length of the foot. The Pythagorean Theorem can help you out. It's the relationship between the lengths of a right triangle's two legs, A and B, and the length of its hypotenuse, C. The equation is a squared plus b squared equals c squared. Here, we can say foot squared plus luff squared equals leech squared. Now, let's figure out that foot. We square luff's length, 240 inches, and the leech's length, 264 inches. Subtract 240 squared from 264 squared. Take the square root of that difference, using a calculator, of course, and we've got a foot of 110 inches to the nearest inch. Bon voyage!